Well, this will wrap up your adventure in organic chemistry lab with a really fun and it could be exciting kind of reaction called the Grignard reaction. The main player in the Grignard reaction is magnesium, so that's what the backdrop is for this slide. Okay, so this is a good time to point out the very close relationship between lecture and lab, because I know you've been learning about electrophiles and nucleophiles in lecture, and you've been actually doing some electrophile meets nucleophile in lab. So, for example, you know cyclohexene is pretty good, well, it's a reasonable nucleophile, and you know that bromine can be an electrophile, so I know that you carried out this reaction. So cyclohexene and most alkenes are nucleophiles, bromine's an electrophile, the proton's an electrophile. You have learned about, I'm sure, the acetylide anion. That's a really nice, strong carbon nucleophile. So all these nucleophiles have a lot of electron density, and the electrophiles don't. They're electron poor. Well, you're about to learn one of the most famous and most useful carbon nucleophiles, and that's the one shown here. This is, in fact, the Grignard reagent. And what you want to focus in on is that bond right there, the bond between a carbon and magnesium. So if you look at it and think about the periodic table, you see that magnesium's really electropositive. Carbon, in that case, because of the polarity of that bond, becomes what? Electronegative. So the way you want to think about a Grignard reagent is that it is a carbanion. So just like my acetylide anion, a Grignard reagent is you think of it as a negatively charged carbon, and that makes it a great nucleophile. That said, it's important that you remember that this great nucleophile is called the Grignard reagent because it was invented by Victor Grignard, who won the Nobel Prize for it. So it is important that you keep that in mind when you write about the Grignard because it's named after good old Victor. So don't forget to capitalize Grignard when you talk about the Grignard reagent. Okay, this experiment actually has several reactions in it. So reaction number 1 is preparation of the Grignard reagent itself. So what you can see is happening here is my metallic magnesium, my zero-valent magnesium, is somehow or other kind of inserting itself in between that carbon and that bromine. So it's just kind of magically happening. And that is exactly how we're going to treat that. We are not going to worry about how this happens. But that's the first reaction in this experiment. Then we take our wonderful carbon nucleophile, our Grignard reagent, and everybody makes the same one, and then we split up into two different groups. One group will react the Grignard with diethyl carbonate. In so doing, that diethyl carbonate reacts with the Grignard to give this alcohol, where we have taken our nucleophile and our electrophile and put those two together. Actually, as you can see, it takes one of these, one electrophile, to two molecules of the nucleophile, actually 3 molecules of the nucleophile, to give you your product. Now this product, the alcohol, actually goes further and spits out the OH group to make your actual dye. So what you can see here is you have extensive conjugation all the way through the molecule, and that makes this molecule absorb electromagnetic radiation in the visible range, and hence it looks violet. It's really such a deep color, it's kind of blue-violet. So everybody makes the same Grignard, but only half the class is going to react the Grignard with diethyl carbonate. The other half of the class is going to react the Grignard with methyl benzoate. And what you can see here is that I have all this piece is from my methyl benzoate, so it only takes 2 moles of my Grignard reagent to react with methyl benzoate, whereas it took 3 to react with my diethyl carbonate. Well, in any case, the outcome is eventually more or less the same. You make this alcohol, then the alcohol gets spit out, and again you have the extended conjugation that gives you a colored product. And it's interesting to note here that the only difference between these two compounds is that substituent right there. In malachite green, we have a hydrogen. In crystal violet, we have the dimethyl amino group. And since you guys have had UV vis, you should be able to understand that, yeah, they would absorb at a different wavelength in the electromagnetic spectrum, and therefore we see different colors. So it's really very cool. How does it happen? Well, mechanism-wise, as I said in the previous slide, we ain't going to worry about the mechanism for the formation of the Grignard. It is beyond the scope of this class. So don't think about a mechanism for formation of the Grignard. But the rest of the stuff, yes, we need to think mechanism because it's nucleophile meets electrophile. So the first thing we're going to do is cross out our counterion and consider this as an anionic nucleophile. And what's going to happen is my nucleophile is going to react with my electrophile to give me, and now I'm just going to substitute this whole thing, that aromatic ring is going to be called AR. So I'm making a new bond between that aromatic ring and my diethyl carbonate. So I get this intermediate, and what you will learn is that the carbon-oxygen double bond is a very strong bond, and it really likes to form. So I kick out one ethoxy group to make this compound. And that looks like a perfectly stable compound, and it is. However, if there is any more of my Grignard reagent around, which there will be because we're adding 3 equivalents relative to the diethyl carbonate, it'll just add again. So that is going to give me this intermediate, and again I'll abbreviate that AR, and what you can see is again I can kick out an ethoxy group to again regenerate this nice strong carbon-oxygen double bond. But wait! I still have one more equivalent of Grignard around, and this is still an electrophile. Therefore, my Grignard will add one more time, but this time there's nothing else that can happen. I will get my O-, but I don't have any more ethoxy groups to kick out. So the only thing that can happen next is for that, let's clear the screen here, to be protonated by our HCl upon workup. So we protonate. That's where we get our proton transfer. Our alcohol is formed. And now I will show you the full aromatic ring because that's the important next step here. Our amino group then, under acidic conditions, We can protonate this again. And I'm just going to skip this step. I'm just going to show that getting protonated. And since I'm running out of room, I'll just go ahead and make that a great leaving group, which gets kicked out. And that takes me straight to crystal violet. There it is. There's my purple product. So you can apply that mechanism to methyl benzoate or diethyl carbonate. I'll probably give you an assignment as to which electrophile you will use so you know which mechanism to write up. All right, so what's so special about this reaction? Well, it's very powerful. We know it's a good reaction. So why is it technically challenging? Well, it's technically challenging because there's a really good electrophile that's around just about all the time, everywhere you go, and that's moisture. What could it go wrong? Well, if you think about it, thinking about the fact that this is an anion, a good nucleophile, if there's any moisture around, what do I end up with? I end up with no more Grignard is basically what I end up with. This is a big frowny face because that is not going to react with my electrophile. That is dead on arrival. You will get nothing happening if you protonate your Grignard. So we have to kind of bend over backwards to make sure that we don't have any moisture in our reaction environment. How do we do that? Well, we do that by making sure that we flame dry our glassware, and that will be demonstrated in the lab, and that we dry our solvent. The solvent has to be specially prepared, and that will be done for you so that when you get to lab, you will be using dry THF. You got to think about the fact that there's more of the solvent present than anything else. So if the solvent isn't dry and has some protons or water floating around in it, there's no way your Grignard's going to work. All right, so how do we do that? How do we make sure we get it dry and keep it dry? Well, as I said, we flame dry, and what you're going to flame dry is all of the round bottom flask, all of this piece, the Claisen head, and that's pretty much it. You do not want to flame dry the condenser because that might make it crack. So you just flame dry all that fuzzy pink part. Then you have to make sure that no moisture gets in. So before you flame dry it, you've actually put on something called a drying tube so that any air that goes back in goes through a column of drying agent. So any moisture is going to get sucked out right here. So it's still an open system. This is just a bunch of porous rocks, if you will. So air can go in and out, but any air going in will be dry. Well, what about right here? Well, that has to be closed to the environment as well. And the way we work that is we put on there a little rubber septum. Okay? And the rubber septum allows you to syringe in liquids. And so you will syringe in the solution of your electrophile in THF. So this is closed, and this is up here, the drying tube is not closed, but it has the drying agent that prevents any moisture from getting in. So, one, flame dry with a drying tube present and a septum, and then of course using our dry solvent, we've covered all the bases. All right, well, what are the procedural changes? These are changes that I've made from the procedure that's outlined in your lab manual. So first of all, we will not be using a hot water bath for obvious reasons. We will be using the thermal well and the power controller, just like you're used to. We'll be heating gently because the Grignard reaction is exothermic, so you don't need very much heat to get it going. We will make sure that we are adding the dry THF, but we're not going to syringe it in, because if we do this quickly, once we have our dry glassware, the amount of moisture that can get in there is going to be minimal. So we'll just go ahead and measure out the THF using dry glassware. Like, I don't mean flame dried glassware, I just mean something that you haven't washed. Just make sure it doesn't have any moisture, any water in it. So you'll measure out your THF in a graduated cylinder that's dry and just pour it into the flask. Then the third procedural change is that we are going to go ahead and make up the solution of the electrophile for you, so you do not need to worry about that. You will go ahead and add 3 mils of the solution. That's it. It's a very exciting lab because there's lots of color changes and neat things happening, and then at the very end you get to see how well your dye works. So we will see you in lab.